All right, so in the last 2 lectures, we talk about the probability and the distribution. Most of them are abstract ideas. And today, we just want to turn to the real world and to see how to analyze the real data set using those probability equipment. So today, I'm gonna talk about how to do the estimation. So when we have a data set, actually we usually do some descriptive statistics to understand the data set first. But we want to do something beyond that, because when we do the data analysis, usually we want to generate some idea about the population. And the data set is just a sample of the population. So how to draw the inference about the population using the samples is our statistical analysis goal. So for the statistical inference, typically, it can be divided into 2 parts. One part is estimation, the other is hypothesis testing. For the estimation, it is mainly about estimating the values of specific population parameters. This is our today's lecture's topic. So say we are interested in the population, average population household salary. This is the population parameter. We want to get some estimates about this parameter. We need to use the estimation techniques. Some other research question is about hypothesis testing. Say we know the general average household salary for the national level is maybe 600,000. And then we want to perform some test about the average household salary for NYC. We want to test whether our NYC have higher average household salary than the national level. To answer this kind of question, we need to perform some hypothesis testing. So we're gonna talk about the techniques for hypothesis testing in the next lecture. Today, we're gonna focusing on the estimation. So for the estimation, there are 2 parts of it. One is point estimation. The other is interval estimation. So sometimes we are interested in obtaining specific values as estimates of our parameters. And these values are referred as point estimates. In some other times, we would like to specify a range within which the parameter values are likely to fall. If the range is narrow, then we may feel our point estimate is good. And these are called interval estimates. So here is that the statistical inference is always from sample to populations. Our goal is to draw some inferences about population. Someone may be asked, since you are interested in the population parameter, why not you just do the scan over everyone in the population? Actually, sometimes it's impossible. Say you are interested in the water quality for the lake in the United States. It's impossible for you to get a sample from every lake in the United States. So we need to draw some water sample from some lakes to study the overall population. Sometimes it's more efficient to conduct some analysis on the sample instead of the whole population. Such like you want to estimate the average household salary, income, then it's not necessary to do the scan about every household in the population. You can just draw some sample, and based on this sample information, you can get pretty much accurate estimate for the population one. So that's why we need to use statistical analysis method to draw some inferences from the sample for the population. Here, before touching on the detailed techniques, let's clarify some notation, some terminology. First, a parameter. When we talk about parameter, it's a number about population. Okay, the parameter is just a number or quantity to describe the characteristics in population. When we talk about statistics, this is a statistic, a number calculated using sample values. So parameter is about population, statistics is about the sample. We want to draw some inferences from statistics calculated from sample about the parameter which describes the population. Okay? So now let's talk about the estimation of population mean. Lots of time we need to estimate the population mean. First of all, we have a sample. We have n sample, x1, x2, up to xn. That's the observed value for those n samples. And we assume those n samples are randomly sampled from a population. And the underlying truth about the population is governed by its mean mu and the variance sigma square. Those population parameters, mu and sigma square, are unknown. We want to estimate them using the sample, x1 up to xn. So how to use the observed sample to estimate mu and sigma square? In the previous lectures, Dr. Brown has told you how to calculate such sample mean and sample standard deviation. See, those parts I assume you have already known. A natural estimator for estimating population mean mu is the sample mean. We just calculate the mean of the sample values. This is gonna be a good estimator for the population mean. And we also calculate the sample standard deviation in this way. This is gonna be a natural estimator for the population standard deviation. So let's focusing on the sample mean first. Why we say it is a good estimator for the population mean? In order to get inference about population mean, there are some other estimators. Say we can sample median is one other option, or the average of the sample maximum and sample minimum is another option. So why we say the sample mean is the best one? And so that in other words, this is the question, giving you an estimator, how good is this estimate? How to evaluate this estimate? So generally, we would like to this sample mean, this estimator for the population mean should be close to the truth, close to the true population mean mu. However, in reality, we don't know the value of mu. We don't know how close is this sample mean to the true population mean. How do we evaluate this estimator? So usually, to evaluate this estimator, we need to study the distribution of this sample mean. So to understand what properties of sample mean make it a desirable estimator of mu, we need to first forget about our particular sample for the moment and consider all possible samples of size n that could have been selected from the population. So the value of this capital X bar, you see I'm using the capital letter, that means this is a random variable. Because we are doing all possible sample with size n from the population, for each sample, we're gonna have one sample mean, right? So generally, we're using this capital X bar to be the random variable. And all the small x1 bar to x2 bar, those are the observed sample mean for each sample size. Then the sampling distribution of x bar is the distribution of this small x bar over all possible samples of size n that could have been selected from the study population. So look at this picture. We are interested to estimate the population mean. And then we could draw the random sample k times. For each time, we can calculate the sample mean, small sample mean, x1 bar up to xk bar, right? The selection of random sample set actually is a random experiment. And then this big X bar, we define it as the sample mean is a random variable. A random variable gonna have its distribution. We can study its sampling distribution of this big X bar based on those small x1 bar to xk bar. Is that okay? So next we're gonna look at what's the distribution of this big X bar looks like. Here's remember here we got capital K small x bar. Then we can draw the histogram over those K sample means. It looks like that. So exactly what kind of distribution for this sample mean it is, here we're gonna show you. First of all, we study some properties of this sample mean. Sample mean is an unbiased estimator of population mean. We can show that the average of all those sample means, those small sample means, is equal to population mean mu. This can be showed by this equation. The expectation of the sample mean equals to the population mean. This means that this sample mean is an unbiased estimator of the population mean. So if you draw a lot of sample size, and for each sample size, you calculate the sample mean. If you take the average of it, if the number of those sample sizes is really large, this is gonna be very close to the true population mean. That means what? When you draw a random sample, calculate the sample mean, this one should be always around the true population mean. Okay? And the unbiasedness of the sample mean is not enough to use it as an estimator of mu. It has another good opportunity to ensure that this sample mean is the best estimator for the population mean. That is, among all kinds of unbiased estimators, the sample mean has the smallest variance. So it's the most less variable estimator for the population mean. The variance is the smallest. We can mathematically prove it. So that's the reason we always use the sample mean to estimate the population mean. Then what's the variance of sample mean x bar? The sample mean x bar, suppose sigma square is the population variance, and the variance of sample mean is sigma square over n. And I can show you how to prove it. So because for each x1 up to xn is from, it has expectation equals to mu, and the variance of x1 is sigma squared. For each of them, it has mean, mu, and the variance sigma squared. Then what's the variance of x bar? That is the variance of 1 over n summation xi, I from 1 to n, right? Inside the parentheses is the sample mean. We are looking at the variance of the sample mean. Then this is equals to what? And here you need to know the fact that if the variance of x is sigma squared, then variance of ax gonna be a squared sigma squared. For the number before it, you need to take the square of it when you calculate the variance. So then this is the parameter before it is 1 over n. That's gonna be equals to 1 over n squared variance of summation xi, I from 1 to n, right? Then for each of them, the variance of summation of xi equals to 1 over n squared summation of variance of xi, I from 1 to n. For each xi, the variance is sigma squared. So you do the summation, then this part is n times sigma squared. So n and n squared cancel out 1n. That is becomes 1 over n sigma squared. That okay? So we can mathematically calculate the variance of sample mean is just the population variance divided by n. And the standard error of sample mean is sigma divided by square root of n. Here, I want to draw your attention about this part. 1 over square root of n, this is a very important factor. It's gonna be occur lots of time in the statistical inferences. So for the sample mean, the variance of the sample mean is related to the population variance with the adjustment of this factor, 1 over square root of n. So the sample size, if this is related to the sample size, intuitively, if the sample size is large, then your sample mean is more accurate, right? If you have more sample in your samples, you can get a more accurate, more accurate sample mean estimator, and this estimator has smaller standard error, right? So this is the standard error of sample mean. And in that formula, you can see this is related to the population variance, sigma squared. Usually this is unknown. So when we want to use that formula, we need to replace sigma squared or sigma by the sample standard error or sample standard deviation, S. So the formula for S is given like that. So from this derivation for the standard error for the sample mean, you can see the larger sample size is, the smaller standard error is, and the more accurate estimation for the sample mean. Is that okay? So here is an example to calculate the standard error. Given you a sample with 10 birth weights, and using some software or some calculator, you can quickly calculate the sample mean. Small x bar is 117, and the sample standard deviation is 22.44. So in order to estimate the population mean mu, we first get a point estimate. Actually, the sample mean small x bar, just the point estimate for the population mean. And its standard error should be calculated by the sample standard deviation divided by square root of n. Here n equals to 10. You need to use 22.44 divided by square root of 10. 7.09 is the standard error for this sample mean. When you report the point estimates, just report the estimate itself is not enough, because for that, this is just an estimate for a point. You don't know how accurate for these estimates. You need to always to report its standard error. Is that okay?
Can you explain a bit what the differences between standard deviation and standard error?
Standard error standard deviation is a kind of general. When we call standard deviation, we usually use sigma. This is the parameter, the population parameter. Then if we calculate the standard error using the sample, we call it sample standard deviation or sample standard error. That is to describe the variability among the sample. And then because we propose a sample mean as an estimator, it is actually a random variable. For random variable, we can calculate its variance or standard deviation. So just for the standard deviation for statistics, for the sample mean, we call it standard error. Is that okay? So because previously we talked about big X bar is actually a random variable, because the selection of the sample is kind of random experiment. We define a random variable, then a random variable should have its variance. And this variance, has the relationship between the underlying standard deviation or standard error. And we use the standard error here just to refer to the standard error of big X bar, the sample mean, for this variable. For this random variable, actually it's a statistics based on the sample values. What's the standard error for this random variable? Do you still confused about these definitions? Such like you look at that formula. Here, x, we know x have mean mu and a variance sigma square. Those are the population parameters. For each variable, for each number in the population, it has such property. Its variance is sigma squared. But this is just for one single sample. We draw a sample, we keep doing that. The variance of the value for this sample in the population is sigma squared. And then we draw a set of samples, we have n sample. Just using those n sample, we can calculate the sample variance. That's gonna be S squared. S squared actually is the estimator for sigma squared. The S squared gonna be estimate sigma squared. But now we are talking about big capital X bar. X bar is defined by the sample mean. It's the summation of all the observations from the samples. And this is also a random variable. And what's the variance for it? It's 1 over n times sigma squared. Then we take the square root of it. This is we define as the standard error for X bar. Sigma squared is just for X in the population. Is that okay? Yes.
Could you just go over again the difference between X bar and big X bar?
You mean
Is it the average of other averages?
square root of n?
Or like just like a regular X bar and then you said there's a capital X bar?
1 over square root of n times s. This is the standard error for capital X bar. For the random variable, only a random variable has the variance. If it's a small x, that's just an observation. A specific value is certain. There's no randomness for it. So there's no variance for the small x. It's always for the random variable. We have the randomness. We need to using the standard error to measure how spread are this value for this random variable.
So where did the capital X bar come from?
Capital X, you remember this picture? So here, in order to estimate the population mean, we need to draw a sample from the population. Actually, we can draw multiple samples with the sample size n. So for each sample, we can calculate the sample mean. That is the observed value for big X bar. And we're using this capital X bar just to represent a random variable to represent the sample mean for each possible sample with size n. Okay?
I think that's maybe where the confusion is for a few of us. So if you go back to that slide again. So big X bar you're describing as the population mean? And
No.
Small, because you decided you have random samplings taken of small X bar 1, small X bar 2. So to me, this reads a selection of a random sample. So the population mean is a derivative of it's an average of the random samplings that you
Population mean I'm using mu to denote the population mean. This capital X bar just the random variable for sample mean. Just like if I toss a die, then I'm using X to denote its face-up value. This X could be 1, 2, 3, 4, 5, 6. And I use capital X bar to denote the sample mean because once I draw a sample with size n, I calculate the sample mean of it. The one possible value is small x1 bar. And then the second I draw another sample with size n, I got a small x2 bar. So this capital X bar just represents a sample mean. This is a random variable. This is a general random variable for all the samples.
So your population mean is different from large X bar, which would be the average of the random samplings that you take. Small X bar would be a single sample.
Right, yeah. So in general, I say this capital X bar is a good estimator for mu. Then given you a specific sample, you can get a specific sample calculate for the population mean. Then this capital X bar is a random variable, and what's general because it has a distribution. The distribution can be, I just show you, if you just draw all the possible sample with sample size n, you can draw this histogram. This is actually the empirical distribution for capital X bar. And then there is the standard error or variance for capital X bar. Just now, I just show you for this capital X bar, the standard error for it is sigma divided by square root of n. This formula just show you the standard error or the variance for capital X bar, this sample mean variable, is related to the population variance sigma. What's the relationship? It's just always using the population variance divided by square root of n. It's related to the sample size. The more sample you draw, the more accurate for this capital X bar. Okay? So here, just giving you a sample, you can calculate the sample mean and its standard error. So here's the summary of sampling distribution of this sample mean. Let x1 to xn be a random sample from a population with a mean mu and a variance sigma square. Then the mean and the variance of x bar is mu and sigma square divided by n. We just derived it in the previous slides. Yes?
Sorry, I have a question regarding the standard deviation from the previous slide.
Okay.
Sorry, so for the mean, the big X bar is a few samples and the mean from the means of the different samples. So regarding the standard deviation, do you look at just one standard deviation for one sample, or is the standard deviation from multiple samples that you do?
So for this problem, it just gives you a specific sample size.
One sample, right?
Yeah, just one sample.
But then
And
when you are trying to look at population, are you supposed to use multiple samples standard deviation because you use the multiple samples mean to estimate a population mean. So
yeah, here, giving you a sample, you can first calculate the sample mean from this sample and also sample standard deviation from this specific sample.
Yeah.
And then we just using the calculated S squared, this is sample standard deviation, to estimate the population variance sigma squared. So in reality, actually you always analyze one specific data set, just one sample.
then what's the point with the mean of multiple samples?
That is,
It's just an explanation.
just explanation to show you this X bar, big capital X bar, actually represent a random variable. It has its inherent variance related to the population variance. And then when you do the data analysis, you always analyze one set of sample. And then from that set of sample, you can using the sample mean and the sample variance to estimate the population mean and the population variance. After you get the estimate for the population variance, you can associate it with the standard error for capital X bar. That is the random variable for sample mean. Is that okay? So back to the summary of the sampling distribution of this sample mean. If x1 up to xn be a random sample from a normal population with mean mu and sigma square, then by the properties of linear combination, so if we know the underlying population model for x, for those single x, are normal, then the sample mean, capital X bar, should also be normal. That's gonna be very good because we understand the normal distribution very well. We know normal distribution has lots of good properties. We're gonna apply those properties to X bar directly because if we know the underlying population model for those X are normal, we know X bar actually is normally distributed with a mean mu and a sigma squared divided by n by its variance. This part, is that okay? So underlying population is normal, then X bar is normal. Then we can using the normal property to to draw the inference about the sample mean. So now the question is that if the population is not normal, actually in reality, most of the time, the underlying population is not normally distributed. So what's the distribution of this sample mean? I'm gonna tell you, it's still normally distributed. This is so cool, right? So this is all because this central limit theorem. Let x1, x2, up to xn denote n independent random variable samples from some population with mean mu and variance sigma squared. If n is very large, you can notice those two underlying conditions for central limit theorem. All of those n samples are independent, and n is very large. Then the sampling distribution of the sample mean x bar is approximately normally distributed, even if the underlying population is not normal. Is that okay? So as the sample mean x bar, if those two conditions, independent sample and n is large, is satisfied, the x bar is always approximately normally distributed with mean mu, the population mean, and standard error is sigma over square root of n. So if we know this quantity is normally distributed, we can do some transformation to show that this quantity minus mean divided by standard error is a standard normal distributed. So all the following statistical inferences is based on this normal distribution. So far you understand this x bar by central limit theorem is always normally distributed as long as the sample size is very large and all individual samples are independently drawn from the population. You understand that, right? Okay, yes?
It sounds like you're making artificial normal distribution, even though the population distribution is not normal. Then how would you correctly interpret or predict the population distribution?
It's not artificially. It's mathematically proved by this central limit theorem. When n is really large, the sample mean is normally distributed. And for here, I'm not predict or estimate the population distribution. I'm estimating the population mean, okay? So I just want to estimate the population mean. Actually, I want to use this sample mean to estimate the population mean. And what I'm saying right now is just the underlying reason why I want to use sample mean to estimate population mean. Why I don't use the sample median or sample max plus sample minimum divided by 2 to estimate the population mean, okay? Okay, so here, this picture just to show you the central limit theorem, the power of central limit theorem. Picture A is the underlying population distribution. You can see this is not normal. It's not normal at all. It's not symmetric. It's monotone. And then I draw sample. Picture B, for each time, I just draw 2 samples from the population, calculate the sample mean over those 2 samples, and then I repeat it a couple times, and I can get the empirical distribution for this small x bar. For this x bar, the sample mean. You see the picture of it is still not normal, right? And then I increase the sample size. For each time, I draw 10 samples, calculate the sample mean, repeat it multiple times, and draw the empirical histogram for this x bar. It's more like to be a normal. I continue increase the sample size to 25, then the sampling distribution for x bar for this sample mean is almost like a normal. That is the beauty of the central limit theorem. When n is large enough, the sampling distribution for the sample mean is approximately like a normal distribution, although the underlying population is not normal at all. Is that okay? So we're gonna using this normal distribution to build up an interval estimate for the population mean. Let x1, x2, xn denote n independent random variables sampled from some population with mean mu and variance sigma square. Our goal is to estimate mu, the population mean, We already know X bar is a good point estimate. Next, we're gonna construct an interval estimate for mu. This interval estimate should have the format for sample mean X bar minus A plus A. So we put the sample mean as the center and then expand it to A, to the distance of A to both sides. This is gonna give you an interval estimate, such like a 95% confidence interval for mu should satisfy this equation. The probability, if we call this interval X bar minus A to X bar plus A, have 95%, it's a 95% confidence interval, then the probability of the true population mean fall into this interval its probability should be 95%. In practice, what's the meaning of the 95% confidence interval is that we draw a large number of times of sample with size n. For each time, we're using this technique to get an interval estimate. So among those large time of samples, say once we repeated 1,000 times, about 95% of them cover the true population mean mu. That means the 95% confidence interval. It's not about a simple sample size or simple sample confidence interval, another simple interval estimate. Because given you a sample, you get this interval estimate. If you know the truth, then the truth is either in the interval or not in the interval. When I talk about 95% confidence interval, it's about you repeated this technique, this sampling procedure, a very large number of times, say 10,000 times. About those 10,000 times, each time you use the same technique to create this 95% interval, then among those large number of times, there are about 95% of those cover the true population mean. This is the meaning of 95% confidence interval. So how to get it? Here we just using this normal distribution for this sampling mean. Just now I show you by central limit theorem, we have sample mean X bar is normally distributed. Using the Z, the standardized transformation, we have the Z statistics. So minus the population, minus its mean and divided by its standard deviation or standard error. So we know this is a standard normal distribution. So for standard normal distribution, recall to this picture. We know that for a standard normal distribution, there are about 68% of the data fall into the interval from -1 to 1. Right? Last lecture, I showed you for the standard normal distribution. We have such facts. For the standard normal distribution, the probability for Z between -1 to 1 is 68%. And for the Z between -1.96 to 1.96 is 95%. We just want to apply these facts to construct the 95% confidence interval. So since we know the probability of Z is a value between -1.96 to +1.96 is 95%, we replace Z by this sampling mean quantity, capital X bar minus mu divided by standard error. It's also, because this is a standard normal distributed, so this quantity is between, the probability for this quantity between -1.96 to +1.96 is 95%. And in this formula for the sigma is the population standard deviation. We don't know it, so we just replace sigma by S, the sample standard deviation. Then we get this quantity, this equation. And from this equation, after some arrangement, you will get the probability for mu greater or equal to sample mean minus 1.96 multiply its sample standard error of sampling mean, and the upper end is sample mean plus 1.96 times the standard error of sample mean. This interval gives you 95% confidence interval. Is there any question from this step to this step? You just do some calculations from X bar. You can see here. We have 0.95 equals to probability negative 1.96. That's all equal then X bar minus mu divided by S over square root of n. That's all equal than 1.96. And this part actually you can write it mu minus X bar divided by S over square root of n, greater or equal than negative 1.696. That's all equal to then 1.96, right? You just flip the order for X bar and mu. It doesn't change because here is negative, this is positive, this is symmetric. And then you plus X, you multiply the denominator on 3 terms together. You get negative 1.96 times S over square root of n. That's all equal then mu minus X bar. That's all equal then 1.96 times S over square root of n, right? Then you plus X bar on those 3 terms together. You get, here is X bar minus it. Then minus X bar plus X bar is cancelled out. Then here is X bar plus this term. This is the 95% confidence interval for population mean. So this way, we derive the formula for 95% confidence interval for population mean. Here is the example. Assuming we are taking 92 student samples from NYU student population, and the sample mean weight is 145.2 pounds, and the sample standard deviation, that is small s, is 23.7. What's the 95% confidence interval for NYU student mean weight? So this is asking you to construct a 95% confidence interval for the population mean mu. So this problem is simple. You just need to apply the formula we just derived from the last slide. First of all, you need to first calculate the standard error. The standard error for sample mean is just the sample deviation divided by square root of n. In this example, you know n is 92. You just use 23.7 divided by square root of 92. You get the standard error for X bar. Then you plug in the number in the formula. You get the confidence interval in this way. So finally, you get the interval estimates. Any questions? Here, this is the 95% confidence interval for population mean. Then what's the general interval estimation for an arbitrary level of confidence 1 minus alpha? So if we are asking for 95% confidence interval, alpha gonna be 5%, because 1 minus it equals to the number we are talking about. 95% alpha gonna be 5%. So to derive the general formula for this arbitrary level of confidence 1 minus alpha, you need to look at this, the distribution picture for the standard normal. So we are looking at the confidence interval with confidence 1 minus alpha. That we are looking at an interval, the probability for this interval to cover the true population mean should be equals to 1 minus alpha. We're gonna cut out the 2 little tails from the standard normal distribution, only looking at the center part. We are creating the interval estimate just make the sample mean as the center and extend it to a distance to two sides. So here, if we are looking for an interval has confidence 1 minus alpha, then we need to cut out those two small tails, each with the probability alpha over 2. Is that okay? So then we are looking at these two critical values, z alpha over 2 and z 1 minus alpha over 2. The absolute value for those two parts should be equal because normal distribution is symmetric. So we only need to figure out one value, one critical value. This critical value, z alpha over 2, satisfies the following condition. The probability of a standard normal less or equal to this critical value with alpha over 2 be its probability, the probability should be alpha over 2. And in particularly, if we want to looking at 95% confidence interval, we need to first figure out what's the z 0.025, what's the value for this critical point. And we need to find z, this value, satisfy this equation. How to find out this value? You can using, in Excel, you can using this function, norm inverse. And for this function, there are 3 parameters. The first parameter is just a probability. The probability is the left probability. For the probability of standard normal less or equal than this value, the probability should be 0.025 in this particularly calculation. So in particularly, if we want to find out z 0.025, we just using this function, put a probability 0.025 in the first elements. The second element is just a mean because it's standard normal, the mean has 0. And the third element is the standard deviation. For standard normal, the standard deviation is 1. So just put 0, 1 there. It's just a respond to you this critical value, z alpha over 2 should be negative 1.96. Then you will know that you will use this number to construct a confidence interval to give you 95% confidence. So here I just summarize all of those commonly used z critical values in this table. So usually 95% confidence interval is the conventional one people used in research or in their publication. We always report 95% confidence interval. Sometimes we would like to estimate 90% confidence interval or 80% confidence interval. Sometimes we're looking at 99% confidence interval. Those are just a commonly used number for confidence interval. Here, 1 minus alpha, just a confidence level, and then in the last row, it gives you the critical values. So how to use this table? If you want to construct a 99% confidence interval, you just using this critical value for z, 2.58. So for 99% level of confidence, you go out 2.58 standard error from its sample mean. This gives you 99% confidence interval. So here's the summarize. Generally, how to construct a confidence interval for population mean. 100% multiply 1 minus alpha confidence interval for population mean mu of a normal distribution with unknown variance is given by this one. So you start from the sample mean plus or minus by a quantity. This quantity is defined by the critical value you obtained from the z, the standard normal distribution from the table in the previous slides, corresponding to the right confidence level, multiply the standard error for the sample mean. The standard error is defined by the sample standard deviation divided by square root of n. you should be able to calculate it using the sample you are given. Is that okay? So this is the general formula for the 1 minus alpha 100% confidence interval for the population mean. Any questions? So here, you can see I put a note in the title. This is only true when n is large, because central limit theorem, all of this is based on the central limit theorem. Central limit theorem has one condition, is the sample size is large. So what happens if sample size is small? How small is small? I told you 30 is usually a magic number. If the sample size beyond 30, you can be safe to use the central limit theorem using the normal distribution to construct your confidence interval. If your sample size is small, whenever it's less than 30, you cannot use the central limit theorem. Here, I will show you which distribution, which method you need to use to draw the inference. One sample size is smaller than 30. This quantity, you cannot approximate it. It cannot be approximated by normal distribution. Actually, it is distributed like a student t distribution. So next, I'm gonna show you what is student t distribution. So for small n, usually less than 30, the central limit theorem doesn't stand, so we need to use the student t distribution. For this quantity, when the sample size is small, actually, this quantity is always distributed as a t distribution with degree of freedom. This t distribution has one parameter, degree of freedom, because this t distribution associated with sample size. So n is your sample size. Then this quantity gonna distribute it as t distribution with degree of freedom n minus 1. And in this formula, S just a standard deviation from your sample. And here, the picture shows you the difference between t distribution and the normal distribution. The solid line are normal distribution. And those two dashed lines are t distribution. And this one is t distribution with 2 degrees of freedom. And the one in the middle here is with 9 degrees of freedom. So generally, you can see t distribution have fatter tails than the normal distribution, right? On the tails, this is t distribution has fatter tails. T distribution is more spread out than the normal distribution. Is that okay? But you can see as the sample size increases, as this degree of freedom goes up, this t distribution is more and more looks like the normal distribution. So that is why when n is large enough, then we can using the normal distribution to approximate the t distribution. Because when n is very large, t actually is the same as the normal distribution. Okay? So if n is the sample size, the corresponding t distribution has n minus 1 degree of freedom. So when you talk about t distribution, you always need to know what's the degree of freedom. The degree of freedom is determined by the sample size minus 1. Why we minus 1? Why we lose 1 degree of freedom? Because recall that in the formula, we use the sample mean to estimate the population mean. In here, we just use up 1 degree of freedom. We use the sample one time, so this quantity, when we talk about the degree of freedom, we need to minus 1. So for t distribution, it has n minus 1 degree of freedom. Then this table just comparing the 97.5 percentile for the t distribution with the normal distribution. The table just show you as the degree of freedom goes up, and this t distribution on the tail, we're just looking at one data point. It shows you t is approximating the normal distribution. As the sample size increases, t is more and more like the normal distribution. You can see the 97.5 percentile for the normal distribution. This critical value is always 1.96, right? And for the t distribution, 1 degree of freedom is 4. This critical value is 2.7. It's much larger than the z value, the normal value. But as the degree of freedom increase to infinity to a very large number, this number is very close. It's almost identical to normal distribution.
In 60,
Mm-hmm.
degrees of freedom is 60, you can use the
Yeah, you can use, yeah, right, you can use the similar. You can see this number is quite small. The difference is quite small, right? 2 and 1.96. 1.96 is almost 2. It's usually need to multiply the standard error. Standard error is an even smaller number. So the approximation, right? This is approximation. The difference is minor. So actually when you see when D is 29, the sample size is 30. T distribution is 2.045. Actually, it's already very close to the normal value. So from this table, you can see the bigger degrees of freedom, the closer to the standard normal distribution. And also, T distribution is more spread out than normal distribution. And this T critical value is more farther from 0 than the Z value. So now we know that quantity, this sample mean, that standardized sample mean, follow a T distribution instead of normal distribution. So the only difference here, we need to figure out the critical value from T distribution instead of normal distribution. So same idea, we need to find out these two critical values. These two critical values, the absolute value of them should be the same because T distribution also symmetric. And how to find out this critical value, you need to use this probability statement. We know for a variable follow to a T distribution with degree of freedom n-1, the probability for it greater than this critical value at the probability 1 minus alpha over 2 is alpha over 2. This part is talking about this right tail, right? The probability greater than this critical value is this part. The area of this part is alpha over 2. You can using the T inverse function in Excel to find out the critical value for this T n-1, 1 minus alpha over 2. So obviously, you need to give the probability 0.025 as the first element in this function. And the second element is just the degree of freedom for this T distribution you are talking about. Okay? So using this function, you can find out the critical value for the T distribution. Then the confidence interval for the mean of a normal distribution is constructed like this. The only difference from this one with the large sample size one is you replace the critical value from the normal distribution by the one from the T distribution. All the others are the same. Is that okay? So then we want to talk about the factors affecting the length of confidence interval, right? Presumably, yeah, actually, when you talk about confidence interval, you always hope your interval has shorter length. That means your point estimate is very accurate. The smaller of the length of your confidence interval, the more accurate of your point estimates. So which factors affecting this length of confidence interval? The length of confidence interval from the formula, talking about that one from the T distribution, just equals to 2 multiply this critical value times the standard error, right? For this confidence interval, the length of it, just 2 times this part, this margin, error margin, okay? The length of the confidence interval. So in order to find out which factor affected this length, you're just looking at this formula. In this formula, this length actually is determined by n, the sample size, here in the denominator. S is the standard deviation for the sample, and the alpha is the confidence, the desired confidence you want to construct for your interval. N is the sample size. When the sample size increases, your sample mean has smaller standard error. The point estimator is more accurate. Then the confidence interval has shorter length. Is that okay? So sample size is large, then the length is shorter. S is the standard deviation for the sample, but actually we use it to estimate the population variance. This actually indicates the variability of the distribution of individual observations. So that is, say, in the population, the one you are estimating, if in the population this measurement is very variable, it's spread out, then you're using the sample draw from the population to create the 95% confidence interval, the length should be larger. If in the general population, all the values are very concentrated, so that is less spread out. You draw the sample from it, then you can create a very shorter confidence interval from the sample mean. So S actually is the variability of the distribution from the population. This is also affect the length of your confidence interval. The last factor is the confidence level you desired, either 80% and 99%. Of course, 99% should have longer length in the interval estimation than the 80% confidence interval, right? If you want to be more confident, you're gonna create a longer confidence interval that is has a higher probability to cover the true population mean in 99% probability. Is that okay? So those are three factors affect the length of confidence interval. So far, we have talked about how to estimate the population mean by point estimate and also for its interval estimates. And we discussed two cases. One case is one sample size is small. The other case is one sample size is large. The last part of today's lecture is estimating the population proportion. So now we are talking about the random variable x follow a binomial distribution. A binomial distribution with number of total trial n and success probability p. And the parameter p is unknown. We want to estimate p, this proportion of success. We consider the following sample proportion of success. From the sample, if x is the number of success from this binomial distribution, using x divided by the total number of trial, this is the sample proportion of success. This is a good estimator for the true population parameter p. Let's just look at it through an example. In this example, you can see the prevalence of malignant melanoma in 45 to 54 years old women in US. Suppose a random sample of 5,000 women is selected, and of whom 28 are found to have disease. So you selected 5,000, a sample with size 5,000. Among them, 28 has the disease. So how to use your sample to estimate the prevalence of the disease in general population? Yeah, you can just use the sample proportion, 28 over 5,000, to estimate this population parameter, right? Yeah, that is the truth. And actually, we can see if X is the number of women with the disease among the N women, and X can be looked at a binomial random variable with parameter N and P. For binomial random variable, we know such properties for it. The mean is NP, variance X is N times P times 1 minus P. Q is 1 minus P, the failure probability. So we are proposing to use the sample proportion of the disease to estimate the population proportion. So P hat is given like that. And we, using the property, we can derive its variance and standard deviation. Variance of this sample proportion is given by P times 1 minus P over N. And after we figure out the standard error for this sampling proportion, we can use that to construct the confidence interval. We need to first look at the point estimate for this P. You can just see here, we're just using the sample proportion to estimate this population success probability. And then we're using the formula we just derived in the last slide. You can see the standard error for this sample proportion is given by this formula, the P hat multiply 1 minus P hat divided by the sample size. So this is the standard error for this point estimate. And if you take a second look of this sample proportion, you will see actually this is the same thing as the sample mean. Because for this sample proportion actually can be rewritten into this formula. This actually shows you the sample proportion is exactly the sample mean. Then all the previous derivation, the calculation, also apply for the sample proportion because it's also a sample mean. All of those, the way to derive the confidence interval, we can apply to the sample proportion. And thus, so this is this part we already know. For this new example, we are talking about the breast cancer here. So if we draw a sample for 10,000 samples, among which there are 400 women are found to have breast cancer. And then we first get the point estimates. Using this 400 divided by 10,000 gets you sample proportion. We use this one to estimate the population proportion. And then we're using this formula. This is P hat multiply 1 minus P hat divided by the sample size. Take the square root. I'm sorry, here is a typo here. Here should be SE, the standard error for P hat, instead of variance, because I took the square root of it. So we got the standard error for the sample proportion. And then next, how to derive the interval estimates. The same thing using the central limit theorem, which we applied to get the confidence interval for the population mean. Because the sampling proportion is also a sample mean, this sample proportion is normally distributed using the central limit theorem, with the mean to be the population mean, and this is their sampling variance. So here is a confidence interval formula for the proportion, population proportion. This is quite similar to that one we derived for large sample for the population mean, right? Just replace the sample mean by the sample proportion and its standard error, standard deviation. Standard error for population mean replaced by the standard error for the sampling proportion. And because here we are talking about a large sample size, we're using the normal approximation. We're using the critical value from the normal, standard normal distribution here. So the confidence interval is given like that. Using that formula, we can construct a 95% confidence interval for the point estimate, for the population proportion for breast cancer in that example. You plug in those numbers, then you get the confidence interval is 3.6% to 4.4%. Yeah, basically this is the point estimate and the confidence interval estimate for the proportion. It's quite similar to that one in the sample mean because the sample proportion actually it is a sample mean. The underlying formula is the same, and here just give you the specific confidence interval estimate for the proportion. So here is a summary. In this lecture, we talk about 3 techniques or 3 recipes for confidence interval. For the first one, the one we just talked, is for large sample proportion. We're using the sample proportion plus minus this critical value multiply standard error of it. And for the large sample population mean, we're using the sample mean plus minus this part you derived from the standard normal distribution. The last one is for the small sample population mean. We just replace the critical value obtained from the Z distribution, the standard normal distribution, by the T distribution. And pay attention to the standard error for those three parts. Each of those standard error is proportional to the magic number 1 over square root of n. This number is very important in the statistics and the probability, and in the later lectures, you will see this number a lot of more times. Is that okay? This number just related your sample size with your standard error. Any questions? If no questions, that's it. And the homework has already posted on the website. It's due this Sunday. Okay?